This is an overview of our chest X-ray disease diagnosis project using deep learning. Our project focuses on the intersection of chest X-ray studies and deep learning methods for computer-aided diagnosis. Chest X-rays are low cost and are very common for radiological studies. Distinguishing various complex chest pathologies is very difficult even for casual human observer, and there is a relative lack of radiology interpretation expertise. Computer-aided diagnosis can help practitioners in labeling and localizing disease. The problem is formulated as a multi-label classification problem, where the input is the raw X-ray image and the output is a vector of possibilities for each pathology. We use ROC curve and their area to evaluate the neural networks we train. Also, we obtain heat maps that localize the pathologies and quantify their accuracies. The dataset we use is from the paper of Wang, and it is publicly available from NIH, and it provides over 100,000 front view X-rays. The dataset is weakly labeled with pathologies for each image. It also comes with ground truth bounding boxes for 1,000 images and their labels, created by radiologists. For data pre-processing, no resizing was performed. The original image size is kept as it is for a larger resolution during disease localization. Different base models required slightly different pre-processing. For example, for VGG, the image color scheme is converted and its values are zero-centered according to the ImageNet dataset. The first model we built uses the UGG16 architecture and Internet weights as the base model. We replaced the base model's full FC layers with a global pooling layer, two fully connected layers using ReLU, and then sigmoid activation. From the learning curve, we note that there is no overfitting. As the training loss decreases, validation loss also decreases. This implies that the model can benefit from additional training. The second model we built used the DensNet as the base model, again trained on ImageNet. We replaced its final layers with a transitional convolution layer, a global pooling layer, and a two fully connected layers as before. To optimize our training time, we froze the parameters from the base model. In the loss curve, we see that the training loss decreases and the validation loss increases. This hints possible overfitting. Here are the ROC curves for both models. As we can see, VGG16 outperforms DensNet. We believe this is because we trained the VGG model on all trainable parameters, whereas the DensNet was trained on about 45% of its total parameters. Note that the VGG model achieves an AOC accuracy up to 0.83. Here we compare the result of our modified VGG16 model with the original paper. Looking at the table result, our AUC is better than the original paper. However, it doesn't tell the whole story as our F1 score is significantly worse. Some classes have an F1 score of 0. This implies that its predictions are all no finding. The original paper uses a weighted cross entropy loss function to emphasize learning on positive instances, which we can include in the future work. Here we discuss our methods for disease localization. We use class activation maps, which are calculated by multiplying the last convolution layer output by the width of the final prediction layer. To localize the disease, we first feed the X-ray image through the network and then retrieve its map, followed by a threshold operation to keep only the high intensity areas. Then we generate a bounding box for the largest high-intensity layer. We then compute the intersection over union and the bounding boxes matrix against the ground truth bounding box. Finally, we aggregate the result to calculate the final accuracy and average false positive for each pathology. Here are two example heat maps which successfully localize the pathology. The white box is the ground truth box, and the green box is our network's prediction. We can see that the network localizes multiple areas in the image, and this is because of the weighted sum of each individual prediction target. If the network correctly predicts true label, then the weight for that output will significant and will create higher intensity for the true location. This table shows the accuracies and the false positive rates for the disease under different thresholds. We see that cardiomegaly achieves high accuracy when the threshold is 0.1, and is because it's a disease that affects a large area, so it's easier to localize. Overall, the accuracy decreases as threshold increase. We believe additional chaining and a larger network can perform similar to the original paper. In conclusion, we have tried to replicate the chest X-ray 8 paper and gained promising results with a AUC up to 0.3 and a disease localization accuracy up to 0.6. Our model could further improved by addressing issues such as limiting training time, limited data, and a simplified pipeline. Thank you.